Imagine space not as a void, but as a vast, restless ocean. Invisible, continuous, bending and flexing with every star and planet it holds. Somewhere in that ocean, according to Einstein's mathematics, might exist something extraordinary. A bridge, a tunnel connecting two distant points in space-time, so warped that stepping through one end could mean emerging billions of light-years away, or perhaps, in another universe entirely. We call these theoretical tunnels wormholes. They're not science fiction. They're solutions, rare, exotic answers to Einstein's equations of general relativity. And for decades, physicists have been torn between two haunting possibilities: that wormholes could exist everywhere, hidden in the deep structure of the cosmos, or that they can never exist at all. To understand what a wormhole really is, we have to abandon almost everything our intuition tells us about distance, direction, and geometry. The space you move through, the time you experience, they're not separate things. They're part of one fabric called space-time, and gravity doesn't simply pull on it, it curves it. A massive star doesn't sit in space. It reshapes the very geometry of reality around it. Light bends. Time slows. Space itself distorts. And in certain mathematical configurations, precise, improbable arrangements of energy and curvature, space-time doesn't just bend, it folds. Picture a sheet of paper with two dots drawn far apart. If you fold the paper so the dots touch, you've built a two-dimensional wormhole. Now imagine that same concept in 4 dimensions. That's what Einstein and his collaborator Nathan Rosen proposed in 1935, the Einstein-Rosen Bridge. It wasn't a science fiction gateway. It was a purely mathematical result that fell naturally out of general relativity. But even from the moment it was written down, it came with a catch. It couldn't stay open. The bridge collapses faster than light could travel through it. To any observer, it would look just like a black hole, a sphere of darkness with an invisible heart where space and time fold into themselves. Nothing passes through. The geometry snaps shut, and yet, the equations whispered of a possibility. That with the right conditions, something beyond ordinary matter, something truly alien, the bridge could hold. A stable, traversable wormhole. If such a thing exists, it would rewrite everything we know about space, time, and causality. But to even imagine one, we first need to ask, what could possibly hold a hole in reality open? A wormhole, if one could exist, faces a single, fatal enemy: gravity itself. Gravity, that ancient sculptor of stars and galaxies, doesn't build bridges, it tears them apart. Every curve of space-time it creates, it wants to collapse. Every tunnel it opens, it wants to pinch shut. If you somehow formed a wormhole, gravity would instantly crush it, sealing both ends faster than light could escape. So, the question physicists asked was simple: what could fight back against gravity? Ordinary matter can't. Not stars, not planets, not even neutron stars. They only make space-time curve further inward. To hold a wormhole open, you'd need something that does the opposite. Matter with negative energy density. Something that pushes space-time outward instead of pulling it in. In physics, we call it exotic matter. Exotic matter isn't antimatter. It's far stranger. Antimatter still has positive mass and obeys the same gravitational rules we do. Exotic matter, on the other hand, would violate the most fundamental assumptions of the universe. It would have negative mass. Push it, and it accelerates toward you. Drop it, and it falls upward. It creates a repulsive gravity field. An anti-gravity effect not through technology, but through pure geometry. According to the equations, this bizarre form of matter could, in theory, prop open the throat of a wormhole and stop it from collapsing. It would act like a cosmic scaffolding, an invisible tension that keeps the fabric of space stretched open against its own will. The only problem? We have absolutely no idea if exotic matter actually exists. But that doesn't mean it's impossible. In fact, quantum mechanics, the other great pillar of modern physics, hints that reality might already be generating it in microscopic amounts. The vacuum of space isn't truly empty. It seethes with virtual particles that pop in and out of existence, pairs of opposites that appear, annihilate, and vanish again, countless times per second. These particles borrow energy from the void itself, just for a moment, and in doing so, they sometimes create regions of negative energy density. We've even observed this in specific quantum experiments, such as the Casimir effect, where two metal plates in a vacuum subtly attract each other because the space between them has less quantum energy than the space outside. That less-than-nothing energy is real, measurable, and, at least mathematically, the same kind of thing you'd need to stabilize a wormhole. But there's a problem lurking deeper. Negative energy can exist, yes, but only in tiny, fragile amounts. And the kind of wormhole we'd need to travel through? It would require enough negative energy to counteract the gravitational force of a star, a quantity so vast it borders on the absurd. Still, physics doesn't close the door entirely. It leaves it cracked open, just enough for imagination to pass through. So if exotic matter could keep a wormhole open, where would such a bridge even lead? To find a wormhole, you'd need to look not in the stars, but in the smallest possible places, far beneath the scale of atoms. Because, according to quantum physics, the universe isn't smooth and continuous when you zoom in enough. It boils. At the smallest conceivable level, around 10 to 35 meters the Planck length, space and time stop behaving like a calm ocean and start acting like a violent sea. This churning chaos is called the quantum foam, a restless, fluctuating landscape of spacetime itself. At that scale, the uncertainty principle, which governs quantum mechanics, applies not only to particles but to space and time. The geometry of the universe randomly twists, collapses, and reforms. Tiny bubbles of warped spacetime appear for a brief instant and disappear again. Miniature tunnels that flicker in and out of existence faster than light can cross an atom. In other words, the early universe might have been filled with microscopic wormholes, so small that even a single atom would dwarf them. This idea first emerged in the 1950s when physicist John Wheeler, the man who coined the term black hole, began exploring what spacetime might look like on quantum scales. He proposed that wormholes weren't rare anomalies, but natural fluctuations of the fabric of reality itself. His equation suggested that the vacuum of space could spontaneously generate space-time foam, riddled with transient wormholes connecting fleeting patches of the universe. Now, if the universe started with such foam, it raises a fascinating question. Could any of those wormholes have survived? After all, the Big Bang wasn't gentle. It was an explosion of unimaginable energy. Temperatures and pressures so extreme that most quantum structures would have been obliterated instantly. But maybe, just maybe, a few were stretched and stabilized as the universe rapidly expanded. Some versions of string theory, our best candidate for unifying gravity and quantum mechanics, even suggest this could have happened. In that model, wormholes could be threaded by cosmic strings, hypothetical filaments of immense energy that could hold open their throats. If true, then our universe might already contain these ancient relics, wormholes that have been expanding with spacetime since the dawn of time. They could connect distant corners of the cosmos, hidden behind the blackness, invisible but real. Maybe one sits quietly in the heart of a galaxy, disguised as a black hole. Maybe others drift in intergalactic space, cold and silent, waiting for someone or something to find them. We wouldn't know. To us, a wormhole and a black hole would look almost identical. Both bend light so intensely that not even photons can escape their gravity. The only difference lies beyond the horizon, a difference no telescope could ever see. If wormholes truly exist, they've mastered the art of disguise. To the human eye, even through our most powerful telescopes, a wormhole would appear identical to a black hole. Both warp light, bend time, and hide their secrets behind an event horizon. But inside, their stories diverge. A black hole, as far as we know, ends in tragedy. A singularity, a point of infinite density where physics itself gives up. But a wormhole could be that same black hole, with a twist. Instead of crushing everything into oblivion, it might bend reality into a tunnel, a bridge that leads somewhere else. The idea isn't just science fiction. Some physicists, including Leonard Susskind and Juan Maldacena, have proposed something called the ER-EPR conjecture. It suggests that every pair of quantumly entangled particles, two particles that share information instantly, even across galaxies, might actually be connected by an unimaginably tiny wormhole. If that's true, then wormholes aren't rare at all. They're the hidden threads of the universe, weaving space and time together at every scale. Every atom, every black hole, every quantum field could be stitched together by countless wormholes, invisible, microscopic bridges holding the cosmos in one continuous whole. But we want something bigger, traversable wormholes, tunnels large enough for a person or even a spacecraft to pass through. Could those exist too? Some scientists have speculated that supermassive black holes, like the one at the center of our galaxy, might actually be wormholes in disguise. These colossal objects, billions of times more massive than the Sun, warp space-time so violently that they could connect distant regions of the universe. Unfortunately, the math isn't kind to us. Under general relativity, wormholes that could be crossed, traversable wormholes, collapse the instant they form. Gravity itself pinches them shut, sealing both ends faster than light can travel through. To keep a wormhole open, you'd need something extraordinary: negative energy. This isn't antimatter. It's far stranger. Negative energy would act as anti-gravity, pushing space apart instead of pulling it together. It's the kind of stuff that could prop open the throat of a wormhole, stabilizing it just enough for something, or someone, to pass through. And while we've never seen negative energy in bulk, we have glimpsed its shadow. The Casimir effect observed in labs creates a tiny negative energy field between two metal plates in a vacuum. It's infinitesimal, but it proves one thing: negative energy isn't just fantasy. It's real physics, waiting to be scaled up. So maybe the real question isn't if wormholes exist. Maybe it's whether we can engineer them. Because if nature doesn't give us the bridges we want, humanity might just build its own. If humanity ever learns how to bend space-time itself, wormholes would be the ultimate test, the line between cosmic ambition and cosmic disaster. The first challenge: energy. To make even a microscopic wormhole stable, you'd need more negative energy than exists in entire galaxies. The math is merciless. According to Einstein's field equations, the larger you want the wormhole, the more the universe fights back. Gravity doesn't want shortcuts. It wants symmetry. Every attempt to punch a hole through space-time is countered by the very laws that hold it together. But science rarely stops at impossible. Physicists like Kip Thorne, who helped design the wormhole model for Interstellar, have proven that, in theory, traversable wormholes could exist without collapsing instantly. If we find a way to generate or trap enough negative energy, exotic matter, vacuum fluctuations, or some as-yet unknown quantum mechanism could make it work. Even then, there's a darker problem. Wormholes may not just bend space, they could bend time. By moving one mouth of a wormhole at near light speed and bringing it back, you could create a time difference between the two ends. Step through one, and you'd emerge in the past. This breaks something deep in physics: causality. The universe is built on cause and effect. If wormholes allow you to change that, paradoxes bloom like cracks in a mirror. Could you destroy your own reason for existing? Could the universe allow such a contradiction at all? Some physicists believe these paradoxes are nature's way of saying no. Quantum fluctuations would likely flood any would-be time machine, collapsing it the instant it's built. Wormholes might simply self-destruct to preserve reality's order. And yet, the dream persists. Because the idea of wormholes isn't just about travel, it's about connection. They represent the human desire to overcome limits, to refuse the idea that any distance is truly uncrossable. Maybe one day, far in the future, we'll learn to manipulate the vacuum itself, sculpting space-time like clay, turning equations into engines. We might open the first true doorway through the universe. Or maybe wormholes are forever out of reach. Mathematical poetry, beautiful but untouchable. Either way, they remind us of something profound, that reality is stranger, deeper, and more mysterious than we can yet imagine. Every star in the night sky, every particle, every heartbeat, they all exist in a universe that might be stitched together by hidden bridges, invisible threads connecting everything to everything else. And perhaps, somewhere in that vast web of space-time, one of those bridges is already waiting,